The most recent lesson we did, which was talking about, what was it talking about? Do you remember? We were comparing sizes of sets, weren't we, right? Yeah, we were talking about infinities. We were comparing the integers with the rationals with the reals and drawing some unusual conclusions, okay? Now, I know some of you right now, your brains kind of hurt, and in fact, some of you disagree with some of the methods I showed you. Okay? I just want to go on record to say that I think both of those things are good, okay? Number one, your brain hurts. I think it's good that your brain hurts if when you're considering all of this stuff, right? And you're noticing there's different kinds of infinity, right? Like our brains don't deal with infinity well. We meet a lot of big things in the universe, large numbers, but we never really encounter infinity. So it's no surprise that if you are really wrestling with these ideas, you start to get a bit of a headache. Actually, if you're probably not getting a bit of a headache, you're probably not thinking hard enough, okay? So I think that's a good thing. Secondly, if you disagree, and I saw people wrote posts and they're like, nah, it's garbage, totally disagree, I think it's a rubbish proof, okay? I also think that's good because if you think back to last Friday, right, what last Friday was about, do you remember we talked about how important disagreement is, okay? Actually, when there's disagreement, that's when you make progress. And you know, things like, say, negative numbers, or irrational numbers, or what was the other one I was going to say? Imaginary numbers, right? All of these, when they were first proposed by some crazy mathematician who thought, I'm just going to break the rules and see what happens, right? They all sparked incredible disagreements, okay? But I think that's good. I've got this quote. It's from one of my favorite authors. You might know him as the person who wrote the Chronicles of Narnia. He did a few other things as well, but that's the most popular thing he's done. He wrote this. When we find difficulty, we may always expect that a discovery awaits us. You can see where he would lie on the whole discovery invention thing. Where there is cover, we hope for game. He means in terms of like hunting, like game hunting. Like, you know, you don't go looking in wide open spaces where things are easy to go and find interesting, unusual things. You go look where it's hard. You go look in like a cave or underneath, like where there's trees and shrubs, where there's places for things to hide. That's where you make the really interesting discoveries, okay? And today we're going to look at another one of those unusual ideas that breaks all the rules, namely division by zero. Yes. Okay? Now, many of you have wanted to tackle this, okay, which has been, I'm really glad that so many of you are enthusiastic to do it. But it's a tricky idea. It's a tricky idea for a lot of reasons. There's a lot of assumptions that go into what you think this is and what you think it means, okay? So, to help you get into this, I'm going to pose a couple of questions to you, okay? First one's not rhetorical. When it comes to matter like science type stuff, okay? What's the basic building block of matter? What's the basic building block? Now, the first answer, and this is sort of early 20th century, I think. The first answer was atoms. Okay. In fact, even the name atoms. Does anyone know what atom means? It's a Greek word. What comes from a Greek word? It comes from, well, the A means, you know, when you put A in front of a word like asymmetric or atheist, or what does it mean?
Singular.
A generally means not, right? So asymmetrical, not symmetrical. Okay. So A means not, and this word comes from the Greek word for cut or divide, right? So you can't chop it up. You can't divide it. It's indivisible. That's kind of the phrase you get. Except
It's not true anymore.
in the 20s and 30s, thanks to Einstein, we discovered actually they kind of are divisible with some pretty disastrous sorts of that's a terrible diagram. This is my mushroom cloud, okay? With some pretty disastrous consequences, right? Atoms can be divided. I'm gonna rub that off because it's bad. Now, when you divide an atom, what do you get? You get subatomic particles like. Before we get there, you get electrons, you get protons, and what was the other one? Neutrons. Good. So, like, we have good reason to not think there's anything below this because we can't see these kinds of things, right? These are too small to see with eyes. You can get a really, really big microscope and you're starting to get towards like the wavelength of light, right? So, can't see them, but we know that they're there. They can be proved experimentally. But then, someone with a bigger machine and more of a research budget decided to say, well, is this as far as it can go? And you can go further, right? What do you get?
Quarks.
You get quarks and like
you get strings.
and leptons and bosons, like the famous Higgs boson, right?
What are they?
Well, this isn't a science lesson, so I'm not going to get too far into it. But suffice to say,
What about neutrinos?
these things. Actually, where are neutrinos on this? Are they on this level? I think they're. I don't know. This is getting out of my depth now. Okay. But here's the point. Okay. We thought these were the smallest things that you could get. Everything was built of these. But you're like, no, there's smaller stuff. There's smaller stuff. And then there's theories about like what these are. If they're strings that are vibrating or whatever, okay? But I think this is as far as we've got at the moment. Does that make sense? So, come in.
To Nikita.
Nikita and who? Do you want to come up? Nikita who?
Oh, it was Anik. I don't know why.
Annex here. And anyone else?
I swear there's one more.
And that's about it.
That's all?
There.
That's you.
Oh, that's right. Okay.
Thank you very much, sir.
Okay, now, ready? Here's where we bring this home to us and where we're going today, okay? Now, I'm going to ask you this question. I don't want you to shout out any answers. I just want you to think about it. Think about what you think your answer will be. And I also want you to think about, just like here, how would you justify your answer? If someone else came up with a different answer to you, how would you convince them, no, the answer is this because. So you think of what your answer is and then think of why, right? So my first question was, what was the basic building block of matter? My next question is, what's the basic building block of maths? Now, I want you to think about it. See if you can come up with an answer in your head. Like, maybe this, maybe that. Go back and forth. If you think you can settle on an answer, do you think you can explain why that's the answer? Okay. Now, I'll give you about 10 more seconds to think about this. I am so confident that I know what most of your answer will be, that I'm going to get you to all, we've done this before, shout it out at the same time. Okay, I'll be really interested to see if there's more than one answer here, okay? I'm reasonably confident you all have the same answer, okay? So I'm gonna count to 3, I'll go 1, 2, 3, go, okay? And then I'm gonna ask you to all say it at the same time. Are you ready?
Can we have a minute to think?
Yeah.
You really want more time? You really want more time?
So there's a question.
I'll give you another 30 seconds.
What, so do you want like one word?
Yeah, I think you should be able. Well, if your answer has more than one word, I'm okay with that. If you think you know why. And I want to know what you think, not what the internet thinks. Boring. Your answer doesn't count anymore. Okay, all right. So the question was, what's the basic building block of maths, right? This is the basic building block of matter. Everything that's made up of stuff is made up of these, okay? What is it for maths? Are you ready? Okay. 1, 2, 3. Okay, all right. Hold on. Now, I think the most common answer I heard was the answer I was expecting, which was numbers. Hands up who said numbers. Okay, that is most of you. If you don't know, you can put your hands down. Who said something different? What else do we have? Yep.
Because I think that maths is part of.
That's interesting. Oh.
Maths is part of the universe.
But is math necessarily part of it? Anyway, I won't get into it, okay?
Maths exists before, like, we made it, and without quarks, we wouldn't be here.
Okay, I'll give that a question mark. I'm not sure where I stand on that one. Different answers?
No, it's not just numbers.
Okay, alright, so hold on. So I've got numbers. That was by far the most common answer. Okay? I had quarks. Okay? I have symbols. Who's got a different answer? 0? So you say a number? Is that, yeah? Okay, anyone else? Yeah? Now, I don't know if you can really say an event is a basic building block. Okay, last one, G. Okay, so thought, I guess. Okay, all right. Now, here's the thing, right? If we went out on the street and we went and conducted the same experiment, okay, I think we would probably get the same kind of representation of this being the most common answer. And I know you can kind of play games with these kinds of things, but in terms of like what we normally think of as maths, I think numbers is a reasonable response. Okay, it's certainly what I thought my response would be, but people way smarter than me, and eventually me when I was convinced and I saw the arguments, disagree. They say, no, this is not it. And the reason why it actually comes to what Brendan said, because numbers, right? Numbers are really just symbols. They're just labels that we've put on things, right? There's actually something much deeper than the numbers, and I'll show you what I mean, okay? I should write one up first. Something like, say, 3, that's a number. Okay. But what is 3? Just like with these, right? You're like, okay, numbers are like adders, but can you dig any further into that and find anything else? And I think you can, right? Because past the label, like if you were trying to explain to like a very, very young child, okay, because young children learn numbers very, very quickly, right? What would you say 3 is? Like if you said, okay, a cat is, and then you're like, here's a cat, okay, right? And you know, a car is, and then you're like, there's a car. Okay? And then you say 3 is, and what would you say?
A number.
And they're like, but what's that?
I hate it when they keep asking why.
Now, I actually think it's not that hard. I think we would mostly do the same thing. I think we would say,
Yeah.
this is 3. Look, see? 1, 2, 3. And they'd be like, well, this is whiteboard markers, right? It's like, whoa, wait, right? This is 3. In the same way that, how do I hold these up? That these are 3. I even have the same colors, that's convenient, okay? Look, I know you see these are whiteboard markers, and these are, you know, toys, cubes, whatever. But the thing that they have in common, right? And the things that they have in common with, say, you know, these, right? The quality, the attribute that they share, that's what 3 is, right? In fact, so what we've got is, right? What I've got is, I'll put it under here, okay? I've got whiteboard markers. I've got these cube things. Beautiful. And what was my last thing? Oh, cups, right. 3 is what these all have in common. Now, hold on a second. We have language for this. We just spent like a good week and a half or 2 weeks developing what the language for these things are. What are these? These are sets, aren't they? These are sets. That's what they are. Well done. Okay? They're sets of, well, the elements in this set are cups, and the elements in this set are, you get the idea. You go way back to what our definition for a set was. It's a collection of objects. We call them elements. Okay? So therefore, deeper than numbers are sets. That's what this is really about. Okay? And then everything flows from there. For instance, what is 2 plus 3? Something simple like that, okay? Now you say, well, it's 5, right? But why is it 5? And I'll tell you why.
Oh, 2 things.
You take a set of 2 things, and you take a set of 3 things, and when you put them together, you have a new set of 5 things, right? Okay, well, how about, I'm running out of hands. How about 4 minus 1? What is 4 minus 1? Well, okay, we know what 4 minus 1 is. But why is 4 minus 1 that? What does that mean in terms of all this?
4 take away.
It means you have a set of 4 things, right? You have a set of 4 things. And you take away a set which has 1 thing, and that leaves you with a set that has 3 things in it, right? So it all comes down to these guys and about counting them. And that's when you get operations, when sets interact.
But what if you get a negative number?
Okay, now, here's the interesting thing, right? It starts with all of this counting of concrete things, right? But then we can say, wait, right? We can do things like this without actually having the things in front of us, right? Because we can develop rules for how this works. For instance, if you have a set of some size and you take away a set which has the same size, then it doesn't matter. You don't need to know how big the sets are. This was like our pairing thing yesterday. You can say you'll have an empty set at the end, right? Or in the same way, if you have a set and then you take away, well, if you take away a set that's bigger, it means you kind of have a set which is, well, it's not there, right? It's like I'm short one. There's one that I can't take away. I'm missing one, okay? And you can rearrange this and you can see how it all works, okay? I mean, you know, I would get this line from a line like this. Sorry, wrong way. If I added 5 to both sides, right? It's internally consistent, it makes sense. This is something I can picture with whiteboard markers and I can extend it to something that I can't picture. But it makes sense, I get one from the other, okay? So this is what addition is, it's putting sets together. This is what subtraction is, it's taking sets apart. Okay, I'm gonna ask you to write a couple of sentences in a second. Addition, subtraction. In this scheme, what would multiplication and division be? Because you can see where I'm heading, right? But I need you to go back and think about these old ideas. You've known them for so long that you've forgotten, why do I believe these things? And why do they mean what they mean? Like, I can do multiplication, I can do division, but why are they that? Okay. So I'm going to give you a couple of minutes. I want you to write out a sentence. Multiplication is, division is, right? And try and fit it in this scheme of what mathematics is really about. I'll give you a couple minutes to have a think about it.